So heating and cooling of buildings. So in chemistry, we go over questions on how the heat is transferred from one liquid to the atmosphere, or how the atmosphere heats up or cools down the liquid inside a cup or something like that. So this is kind of the same situation we're dealing with here, is heating and cooling buildings or heating and cooling objects based off different situations around the environment itself. Okay, so this is kind of a nice one. Again, just going over some more process of how to applications of differential equations. So let's think of a couple things. When it comes to cooling, what are some things that can heat a building up? Okay, so we have the obvious one. It's a heater. We can have the outside air. So if it's 100 degrees outside, if you open up the windows, that's going to heat up the inside of it. We have, well, speaking of like everyday household, we have computers. You turn them on, they generate heat, right, for the components themselves. We have any electronics. And one a lot of people don't really notice or talk about is actually people, right? Body heat. So we have all these external factors that go into actually just heating a building or heating something up, not just a single thing when it comes to it. So when you take general chemistry, you always deal with one thing. But if once you go into organic and follow up and again into this process, for example here, there's a couple more variables involved than just simply just the outside temperature. Okay? So because we have multiple things happening when it comes to heating or cooling an object or things like that, we have some situations, right? Some variables to deal with. Okay, so uh, let's write some stuff down. Typically, we're going to use. Okay, so we're going to let T, capital T of T, be the temperature inside of the building, which for obvious reasons, T for temperature. So the temperature of the people inside this building we're going to call H of T. Okay, so the air conditioning to cool the building will be called U of T, and the outside temperature regulating it was going to be M of T. Okay? So we have a total of 4 different things happening. Okay? The temperature inside the building, the people, the air conditioning, and also the outside temperature itself. Okay? Now, the last function is, or basically all of these functions are always in terms of temperature per unit of time. And that's a key thing, right? So it's a rate. Okay. All right, so all of the followings are using Newton's law of cooling, and that's a key thing going forward. A lot of this is always using Newton's law of cooling. Now, the Newton law of cooling is a perfect way, meaning it's just roughly 1 or 2 factors illustrating the actual temperature raising or increasing depending on what we have. So Newton's law of cooling and the rate at which the temperature is changing is proportional to the difference between the inside and the outside area. So in other words, this. Remember, M of T is the outside and capital T is the temperature inside the building, which makes sense, right? You subtract them and it's proportional, so we have this constant K dealing with that proportion. So that's the Newton's law of cooling portion. But where does this U of T come into play? So remember, U of T is like the air conditioning or the heating of the temperature itself, so as an alternative portion. Okay, but a couple scenarios when it comes to the subtraction. Okay, now when we have this difference being a positive number, okay, that saying is the outside temperature is greater than the inside temperature, which makes sense, right? So that means it's hotter outside than it actually is inside the building, which is good because the air conditioning is working, right? That represents cooling. Again, obvious reasons, right? So what represents heating is the opposite. So when this is less than 0, meaning the outside temperature is colder than the inside temperature, right? That represents heating. Again, pretty makes obviously makes sense, right, when it comes to that. But again, not as obvious when it comes to the subtraction, but when it comes to actually heating and temperature inside out, how air conditioning and heaters are built, that kind of makes sense now, right? So that situation is we're going to have here. Either going to be a positive or negative depending on the heating and cooling of the building. Now we go into pretty much everything else. How does the human aspect and the air conditioning aspect come into play of this situation. Okay? So putting all of these functions together, we get our very special differential equation. Okay? So this is from Newton's law of cooling, which is what we just talked about right now. And then it's going to be plus this part here. Okay? So this is plus the heat of the temperature of the people, and then plus the temperature of either the air conditioning or the cooling aspect of itself. Okay? Now, H of T is always positive, no matter what, because temperature of the people is going to be, temperature is never going to be negative. That would be bad, right? We always generate heat, we never reduce heat. Okay? However, U of T will change, again, because U of T is either the air conditioner or the heater, depending on what we're trying to do to the building. Okay? So U of T is negative when cooling and positive when heating, and that's a key thing. So cooling is always negative, heating is always a positive. Okay? Now, doing a lot of algebra, we essentially want to solve for T of T. Okay? And solving for this portion, again, or in other words, taking the separation of variables and all the fun stuff, we get this equation right here. Okay? So it's e raised to the kt times the integral of e all of this. Okay? Now, that's our actual general equation for heating or slash cooling. Okay? Or in other words, the temperature inside a building or inside an actual object of it, like a liquid based off everything else around us. Okay? Now, how in the world does it actually come into play? That's a great question. So let's try an example. Let me put this here, going forward. Okay, so suppose at the end of a day, at time t equaling t naught, when people leave the building, the outside temperature stays at a constant m. The additional heating rate h inside the building is 0. So h is 0. And the furnace slash air conditioning rate u is also 0. Determine t of t given the initial condition of t naught of t of t 0 equals that. Bunch of t's everywhere, zeros, right? Okay, so going back up here, right, this is what we're going to be dealing with. We want to find that. Okay, and then back to the initial condition after that. But for now, first the general equation. Okay, so we're given a lot of information. So a lot of it is just a constant or just is basically 0. The first part says h is 0, so we know h of t is going to be 0. We're also told that u of t is also 0. Okay? And we're given that m of t is a constant m naught, right? So it's like constant number, like 5. Okay? So we're given actually all of this. We're given this, this, this already. And now we're just going to plug everything in respectively. Okay? So if we go to our equation, this is going to equal to e raised to the negative kt times the integral of e raised to the kt times k times m of t, which is just constant, so m naught, plus 0 plus 0 dt plus c. And there we go. And now we just simplify as best we can. So this is all gone, so it ends up being just that. Now remember, this is in terms, oh, let me put parentheses here so it'll be easier to understand what's going on. And now we just integrate. So remembering, this is all a constant, because the integral is in terms of t, so right here. So this can just go on the outside. And this is a straight u substitution, u integral, that u equal all of this So therefore du is k, so we divide by k. So this integral ends up being, well, this on the outside, times 1 over k times all of this. Again, the c there, so let me still have that on the outside there. All right, so k's cancel. If I distribute this by this, the first e's also go away. So I'm pretty much left with a nice little equation. So we just get m naught plus e to the negative kt times c. I'll just put the c in the front because the c is still there. So this is our general equation. Now we go back to our initial condition. Our initial condition is basically plug in T naught, get capital T naught. So we just plug in each individually to solve for the C value. And again, now at this point, we just solve for C. So subtracting this over and then pretty much dividing this across, we get C is equal to, and after a little bit of algebra, we get that. Okay. So therefore, our equation looks like this. Plus all of that. And remembering it's this C times this part right here, or actually this general one there. And then when you multiply, you actually add the powers together. So simplifying this together just gives you T naught minus T. Like that. So why don't we do one with actual numbers instead of, a theoretical one. But very similar to what we just did here. Okay. So a cup of coffee initially at 95 degrees cools to 80 degrees in 5 minutes while sitting in a room of temperature 21 degrees Celsius. Determine when the temperature of the coffee will be at 50 degrees Celsius. Okay, so we have this initial part. Okay. So we have at time 0, the temperature is 95 degrees. We're also told at 5 minutes, temperature is also at 80 degrees. So we have a temperature change. Okay, so now we go back to our definitions of each individual case. Okay, so let's write a couple things down. So we have H of t, M of t, U of t. Those are the other three we need, respectively. All right, so first we'll go down the list. H of t is the temperature of people inside the room. Well, we don't have any people inside this coffee cup, so that's going to be 0. Okay. Next one is U of t. U of t is the air conditioning to cool the building in. So we don't have any air conditioning happening here, so that's also 0. And then finally, M is the temperature outside, so the outside temperature. Okay, so the outside temperature is the temperature of the room, which is 21 degrees. So there is what we have so far. Okay. So now again, all we're going to do is plug it into our equation, which is pretty much right here. right? So I'll put it right here. So this K, M of T now is 21, plus H is 0, plus U, which is also 0, and there we go. Okay, so again, simplifying this a little bit. This is just a constant, so again, I'll just leave it out here. 21k e to the tk dt plus c. Which, if you notice, is the same situation we had above. Again, just another simply U substitution rule. So very, very agreeable we've been doing so far. And then finally, distributing. Gives us our general equation. However, we weren't asked to find this. We were asked to find when is the temperature of the coffee bean 50 degrees Celsius. Okay? So first thing is we got to find more than two things now. We got to find out C, but we also have to find K. And how to do that is using our two initial conditions we have here. Okay? So setting time to be 0, we get 95. And then setting time to be 5 and represents to be 80. We get these two conditions, or these two equations. Now the first one's kind of nice because e to the 0 power is just 1. So this ends up being (21) plus c. So subtracting this over, we get the c value is going to be 74, which is nice. We got one of them. And now we get the other one just using logs. So this gives me 80. Subtracting this over gives you, oh, I'll just do that. So subtracting the 21 over already gives you 59. Taking the natural log of both sides, or actually, yeah, we could do that real quick. We could just plug this in already. So let's plug in what C is already. Dividing by 74. And now taking the natural log of both sides. And again, taking ln of this and then divide by -5, we find out that k is approximately 0.045. So now finally, after all of this work, we have our general solution here. So this is T of t is equal to 21 plus 74e raised to the negative 0.045 t. And now we solve what we want. So we want temperature when the coffee is 50 degrees, or in other words, plug in 50, and we just got to regenerate again to solve for t. So again, pretty straightforward. We want t by itself, so subtract this over, then divide by 74, and it's basically the same process here. Take the natural log of both sides and then divide by the k value, which is negative 0.045. And we get the time to be approximately 20.8 minutes. And there we go.